Here's another little bit more complicated example using ease, and I'm going to solve for this parameter, this variable. It's called delta E dot, and that's equal to m dot times P2 minus P1 divided by rho, which is the density, plus 1/2 times the quantity V2 squared minus V1 squared, where V2 and V1 are the two velocities of a fluid flowing through something like a pump. And let's specify a mass flow rate. M dot is equal to 1 kilogram of water per second, for example, flowing through the pump. And a density, water has a density of about 1,000 kilograms per cubic meter. Let's specify the inlet pressure is 100 kilopascal, and the outlet pressure, P2, is equal to 200 kilopascal. And the inlet velocity of the water, the average velocity of the water flowing into the pump, let's say is 1 meter per second. And the outlet velocity, it leaves the pump at a slightly faster speed of 2 meters per second. And as it turns out, the dimensions that we expect for delta E dot are kilowatts. It's actually a unit of power. So let's specify, I've specified the units for a lot of these parameters that we're going to put into this equation. But let's specify some more. We'll click up here to variable info. Click there, and in delta E dot, I expect it to be kilowatts if all my units are okay. And I'll click OK. All the other units are pre-populated for me because I specified them in the code. So let's run it. When I run it, I ought to get a value for delta E dot. So I'll hit solve, and here it gave me all the different values. It's predicting delta E dot is 1.6 kilowatts. One thing that it said, though, is that there's one potential unit problem that was detected, and I'll guarantee you'll make this mistake repeatedly if you're not careful with the units. And it turns out that it's within this parentheses, with this V2 minus V1. What I brought in were meters per second, and what I actually calculated, and I brought in meters per second here, but I accidentally brought in kilopascal for both P2 and P1. So we need to make a correction for this because we're dealing with things like kilowatts and kilopascal in this class. We need to correct, instead of using meters per second here, we need to put in a unit conversion. And when I check the units, it says that indeed I'm off by a factor of 1,000 within this term. So if I made this calculation, if I reported this value, I'm off by a factor of 1,000. So we need to correct for that. We need to make a unit conversion. So I can do that by multiplying this term by a convert function. It's called convert, and I'm going to convert from meters squared per second squared. So v squared, meters per second, I'm squaring each velocity, meters squared per second squared, and it turns out that's equal to, it's dimensionally the same as a kilojoule per kilogram. So I'll close off that parenthesis, and whatever this conversion factor is, it will correct for that. And now when I hit play, or when I hit solve, I don't have any more unit problems, and I actually come up with delta E dot of about 0.1 kilowatts, or about 101.5 watts. So the fact that it does this unit checking for you will save you a number of headaches throughout the semester as you get familiar with this code. And then if I want to, I can go to Windows and click Formatted Equations, and here's my formatted equation. It looks pretty nice. Here's my delta E dot, my mass flow rate of water, the two pressures, its density, plus this 1/2 times V2 squared minus V1 squared. And what's really nice is it shows me this conversion factor. It's multiplying it by 10 to the minus 3 kilojoules per kilogram per meter squared per second squared. So it's a really handy way to make sure it's doing what you think it's doing. So let's make a graph, and we want to figure out what is the outlet velocity that would occur as a function of the mass flow rate of water. So let's say for any given mass flow rate of water, we want to calculate what velocity could this pump eject that water at. And it turns out it's not too simple. I can get rid of, I'm going to use curly braces just to comment this out, and the code will ignore whatever I called for m dot. And I'm going to do the same thing for V2. It will ignore this line in the code. And now what I want to do is make a table, and there's going to be two columns in the table. The first one will be m dot, and the second one will be V2. So I'll click this button up here. It says New Parametric Table. And I'm going to let it run. We're going to let it make this calculation 101 times. And the variables we want to work with are m dot and V2. We're going to add both of those to the table. So it'll be a table with 101 rows. When I click OK, here's my table, m dot in the first column and V2 in the second column. So let's set up some values for V2. So click this down arrow, and I'm going to say we're going to run it from row 1 to row 101. In the first value, let's say V2 is 0 meters per second. And in the second value, we'll say that V2, we'll run it up to 100 meters per second. So I'll click OK. And now it's populated my graph, so runs 1 through 101. If I scroll down, it's plotting my V2 from 0 to 100 meters per second. So let's run this. When I click play, what it's going to do is run this equation with different values of V2. And for each one of these runs, it's going to iteratively solve for m dot. But before we do that, let's specify. We'll need to specify this delta E dot for the pump. So I'll copy this variable. We'll put it down here. And let's say that delta E dot, the pump, has a power output. Let's say it's a 1 kilowatt pump. So now I've got all the different variables, and for each value of V2, it will calculate m dot for me. So I'll click back on the table. When I click play, it iteratively solved. It went through 101 times, and it calculated different values of m dot. And what we can see by scrolling down is that if we wanted our pump to spit out the fluid at a really fast velocity, it can't handle a very high volumetric flow rate or mass flow of water. So when I come back up, a real low flow rate, real high mass flow of water. Let's see what this table looks like graphically. So I'll click Insert New Plot Window, this button up here. So I'll click that, and on my x-axis, on my x-axis I want V2, and on my y-axis I want m dot. And these are all formatting parameters if you like. Sometimes I like a real thick line and a color, a real thick red line for my graph. And I'll click OK, and here's what it spits out. And what this is showing is that for a real small velocity, the pump can handle a large mass flow rate if we expect a real low velocity. But as you increase this velocity, it scales with velocity squared, remember. And if we needed a real high velocity leaving the pump, that pump could only handle a really small mass flow rate. So this will give you an idea of a couple of things that you can do with Engineering Equation Solver, including making some graphs.